Hello, students. I hope in these tough times of COVID and social distancing, you are all trying your best to stay motivated, safe, and happy. I'm Dr. Seema Singh, and you're watching my channel, Bonding with Chemistry. Before we move ahead, I would like to inform that chemistry live classes for standard 9th and 10th students are already running from December 6, 2020. Those class 9th and 10th students who want to undertake a crash course and be exam ready in 30 days can join my next batch starting in the second week of January 2021. To join these classes, you will need to fill up the Google form whose link is provided in the description box below. Please note that these are paid classes and the payment details are mentioned in the description box below and in the video whose link is given in the info section above. Today I will take up an important topic from the chapter Carbon and its Compounds. The topic is the covalent bond. In my next class, I'll take up a small topic, the properties of covalent compounds. So stay tuned to my channel, please subscribe to it and press the bell icon for receiving the latest notifications. We have already learned in the previous chapters how metals and nonmetals form bond by losing and gaining electrons. That is, we have studied the formation of ionic bonds. Ionic bonds are also known as electrovalent bonds. In case you missed that out, please refer to the link provided in the info section above. In this chapter, we will make ourselves aware of another mode of bond formation, which is sharing of electrons. That is, we will learn formation of covalent bond. Since this chapter deals with carbon and its compounds, so our focus will majorly be on learning how carbon forms bond with other atoms of carbon as well as other elements. To understand covalent bonding, let us first understand why carbon cannot form bonds by losing or gaining electrons. That means why carbon does not form ionic bonds. Please note that this question is very important because it has been put up in CBSE examinations. Well, carbon, as we have learned earlier, has an atomic number of 6. Therefore, its electronic configuration is 2, 4. If I have to label the shells, in K shell it has 2 electrons and in L shell it has 4 electrons. The L shell is known as the outermost shell, and we also know that the outermost shell is also known as the valence shell, and the number of electrons in the valence shell are known as the valence electrons. So carbon has 4 valence electrons. Now, what does it mean? It means that since it has 4 electrons in its outermost shell, it needs to either lose 4 electrons and attain a stable duplet just like helium, or gain 4 electrons and achieve a stable octet configuration of that of neon. Let me explain that. Let's go for the first case when carbon with electronic configuration 2, 4 loses 4 electrons. Its configuration will now become equal to 2. In the outermost shell now it has 2 electrons, and this configuration is similar to that of helium, which has 2 electrons in its valence shell. So now carbon has achieved a stable duplet configuration. Let us now understand the second condition where carbon with configuration 2, 4 gains 4 electron. So now it will have a configuration of 2, 8, which is similar to that of nearest noble gas neon, which has 10 electrons and a configuration of 2, 8. Here the octet configuration of carbon is achieved. So you have duplet if it loses 4 electrons and an octet configuration if it gains 4 electrons. But my dear students, both these conditions are not feasible or not possible due to energy considerations. Let us understand what does that mean. We begin with the first case when carbon loses 4 electrons. If carbon could lose 4 valence electrons, it would form a C4 positive ion, a carbocation, an anion with a positive charge. Well, to remove 4 electrons would require a large amount of energy which is not easily available. Let me elaborate this. The positively charged 6 protons in the nucleus of carbon are holding the 6 negatively charged electron, 2 in the inner shell, that is the K shell, and 4 in the outermost shell. Now, as we keep removing electron one by one, let us say we remove this electron, then this, thereafter this, and then this. On removal of each electron, the number of electrons reduces, but the positive charge remains same because you're not doing anything with the proton. So the same positive charge is holding lesser number of electrons, and thus it would hold them more tightly. For instance, you remove just one valence electrons. So now instead of 6 electrons, you have 5 electrons. I'll put a negative sign. But these 5 electrons are being held together by plus 6 protons, right? Now, if I keep removing the valence electrons from 5 to 4, 3, and finally all 4 electrons have been removed, you are left with just 2 electrons, right? So with each removal, the number of protons remains same, so positive charge remains same, but they are now holding less number of electrons and they'll hold it more tightly. To break this force of attraction and keep on removing all 4 electrons would thus need a considerable amount of energy which is not easily available. Thus, carbon cannot form bonds by losing electrons. Let us move on to the next part. What will happen if carbon gains 4 electrons? Then it is going to form C4 negative ion, a carbon ion with a negative charge which is also known as carbon ion. Here too there is a need of very high energy. Why? Well, 4 more electrons. Let me show them. 1, 2, 3 and 4. 4 more electrons have to be accommodated in the same valence shell that already has 4 electrons. Now these electrons are going to repel the incoming electrons, and thus energy required to overcome these forces of repulsions would be also high, which is again not easily available. Moreover, it would be difficult for the nucleus with 6 protons to hold on to now 10 electrons. 6 were already present and 4 additional. So 6 protons are supposed to now hold 10 electrons, which would indeed be difficult. So we see carbon cannot form bond by gaining electrons also. Thus we conclude carbon cannot form bond by losing or gaining electrons. So how does carbon solve this problem? It overcomes this problem by sharing its valence electrons. My dear students, I've already told you during the formation of bonds, only the valence electrons participate. The electrons of inner shells do not participate, whether it is the ionic bond or covalent bond. Always remember this point. Now, carbon can share its valence electrons with atoms of other carbon, as you can see here. This is the overlapping or the sharing region. We'll understand this slowly. Or it can share its valence electrons with atoms of other elements, as you can see here. It is sharing its valence electron with hydrogen atom. This is the overlapping or the sharing region. Well, this bond formed as a result of electron sharing is known as the covalent bond. This one. This is known as the covalent bond. Let us move ahead and learn the formation of this covalent bond. The formation of covalent bond was explained by scientists Langmuir and Lewis. The word covalent can be split into co and valent. Here co means jointly or joint, and valent implies the valence shell. So the essence of the word covalent bond implies that the atoms share their valence, that is the valence shell. And when they're sharing the valence shell, what actually they're going to share? The valence electrons. The electrons are shared between the bonding atoms which may be same, such as hydrogen molecule. Both the bonding or the participating atoms are same, hydrogen. You can see here they are sharing the electrons, the valence electron, or they can be different. For example, in case of methane, the electrons are going to be shared between one carbon atom and 4 hydrogen atoms, as you can see here. This is the sharing or the overlapping region. where their valence electrons are being shared. The participating atoms are generally nonmetals. If you see here, hydrogen is nonmetal, carbon and hydrogen both are nonmetals. Each of the participating atoms contribute either 1, 2, or 3 electrons present in the valence shell to a common pool. Here you can see, let's go by the example of hydrogen. If you see here, each hydrogen has contributed 1 electron. The black one shows the electrons of this hydrogen atom, whereas the red one symbolizes the valence electron of hydrogen number. Let me mark it as 2. So both of them have contributed 1 electron each to a common pool of electrons. You can see this is common pool. This red electron not only belongs to second hydrogen atom, but it also belongs to the first. Similarly, the black electron, which belongs originally to the first hydrogen atom, also now belongs to the second hydrogen atom. So we can say the valence shell that have been contributed to a common pool of electron belongs to both the participating atoms. These electrons are known as shared pair of electrons, and being shared or counted for both the participating atoms help both of them to achieve the stable nearest inert gas configuration. If you look over here, now this hydrogen has 1 and 2, 2 electrons, so its duplet is complete. Similarly, hydrogen atom number 2 has 2 electrons, 1 and 2, and its duplet configuration is achieved. Similarly, if we look in the case of methane, we look at this carbon atom. It has 4 valence electrons. Remember, I'm not showing the inner electrons because for bonding, valence electron participate. So we have 1, 2, 3 and 4 electrons for carbon, and each hydrogen has 1 valence electron, the one shown in red. So we can see, marking it with asterisk, we have each hydrogen atom contributing 1 electron. Now if we look carefully, these are the common pools of electrons. The electrons belongs to both the participating atoms. Let us find out how. Now look at this carbon atom. It has now 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron. So its octet is complete. Looking at each of the hydrogen atom, beginning with this one, it has now 2 electrons. This hydrogen has 2 electrons. This hydrogen has 2 electrons. Even this hydrogen has 2 electrons. So all 4 hydrogens have their duplet complete and carbon has its octet complete. Thus, they've become stable. As energy required for sharing of electrons is very small, these covalent bonds can easily be formed. So we can define covalent bond as the bond formed by mutual contribution and sharing of electrons in the participating atoms. So this was just a general introduction of covalent bond. Let us now take up examples to understand the formation of covalent bond properly. The simplest molecule being that of hydrogen. I've already shown you how hydrogen forms covalent bond. Let me explain the same in a more detailed manner. We all know hydrogen has an atomic number of 1. So its configuration is, in K shell it has 1 electron, and this K shell is also its valence shell, and since 1 electron is present in the valence shell, hydrogen has 1 valence electron. Since hydrogen molecule has a formula of H2, so I'm going to show the other hydrogen atom with the blue ink. Again it has a configuration of 1. My dear students, now I'm going to draw the Lewis dot structures for hydrogen atom. I've already explained how to draw the Lewis dot structure of simple molecules and compound in one of my previous videos whose link is provided on the top. Please note, you will be studying how to write Lewis structure in greater details in higher classes. There you're going to be taught the rules for writing Lewis dot structures. So for hydrogen, the Lewis dot structure will be the symbol of the element and the valence electron has to be shown by dots. So since it has 1 valence electron, I am showing 1 dot. Please note that you can depict the valence electron by both dots and crosses like this, either dots or crosses as per NCERT. I will be using dots with inks of different colors so as to help you differentiate the valence electrons of the different participating atoms. That means I'll be using dots throughout. The only thing which I'm going to do is change the color. For instance, the Lewis dot structure for this hydrogen atom I'm going to show by blue ink, H and 1 electron. Now my dear students, if you look carefully, hydrogen has 1 electron. in order to obtain the nearest noble gas configuration. What is the nearest noble gas? Helium. Helium has a configuration of two valence electrons in its k shell. This hydrogen needs one electron. Even this hydrogen needs one electron. What do? They will share. They will come close. So each of them is going to contribute its single valence electron. They're going to share their valence electron. How? See here. They'll come close. This hydrogen is sharing this electron. Similarly, this hydrogen atom, the one I've shown in blue, is sharing its electron. They're coming close. Now these pair of electron, how many pair of electron are there? One pair of electron. They are common to both the hydrogen. Let us see, are they able to achieve a duplet configuration? Look at this hydrogen atom. It has two electrons. So its duplet is complete like that of helium. Look at this hydrogen atom. It also has now two electrons in its valence shell, right? So its duplet configuration is also complete. This is the common pool of shared pair of electrons. So here these two electrons do not belong completely to this hydrogen atom or this hydrogen atom. They are being shared. It is just like, let me give you an example from everyday life. It's December month and it's chilling cold in the north. We have two poor people out there in the street. They have just one quilt. Let us say this is the first person and this is the second person. It is biting cold, it is chilling cold, right? And both of them have just one quilt. Now both of them want to save themselves from the cold. What do? If this person takes the quilt completely, then this person will be shivering. If this person takes it completely, then this person will be left out. What do? They will share. They'll come close and they are going to share the quilt, right? So the quilt doesn't belongs to this person or this person completely. They are sharing the quilt and thus they are both able to save themselves from the biting cold. I know it is very difficult to share just one quilt and save yourself from the cold, but only for explanation part I've taken this example. So schematically, the formation of hydrogen molecule can be illustrated as this. Each of the participating hydrogen atom has one valence electron, which it contributes to the common pool of electrons, and thus a bond is formed between the two hydrogen atom, which is known as the covalent bond. Let me give you one more example where the participating atoms for covalent bond formation are different. Example, methane, whose chemical formula is CH4. So we have one carbon atom and four hydrogen atom. Let's draw the Lewis structure for carbon and hydrogen. Carbon has atomic number 6 with configuration 2, 4. It has 4 valence electron. So I'm going to represent the Lewis dot structure for carbon as the symbol C and 4 electrons in 4 different directions shown by dots. For hydrogen, we already know how to draw the Lewis dot structure, a hydrogen with a single valence electron. Now, since we have 4 hydrogen atoms, we are going to place them in 4 different directions around carbon. Let's see how. So we have one hydrogen here. Let's put the other 3 on 3 different sides of carbon, and these are their electrons. Now let us find out whether carbon and hydrogen on sharing electrons have been able to achieve octet and duplet configuration respectively. First let us look at carbon. Now here carbon and hydrogen are the participating atom. Both of them have shared one electron. Carbon is giving its one electron here and hydrogen is giving its one electron in the common electron pool. So they are sharing one pair of electron. Here we have this hydrogen and carbon as the participating atom. Here we have this carbon and this hydrogen, and here this carbon and this hydrogen. Now carbon is having 1, 2, 3, 4 valence electron of its own. One this hydrogen is given, one this, and one this hydrogen. So it has 1, 2, 3, 4, 5, 6, 7, 8. So carbon has been able to successfully obtain or achieve its octet configuration. And that octet configuration is going to be similar to that of the nearest noble gas, neon. Coming on to hydrogen. Each hydrogen requires one more electron to complete its duplet. So this hydrogen is having one its own electron and one from carbon. So its duplet is complete. Coming on to this hydrogen, its duplet is also complete. The duplet of this hydrogen is also complete, and the duplet of this fourth hydrogen is also complete. So we see carbon has been able to achieve the octet configuration, whereas hydrogen, the nearest noble gas, helium's duplet configuration. Thus, all the participating atoms have been able to achieve a stable configuration. So, if I have to show it schematically, we have carbon with 4 valence electron, hydrogen with 1 electron. There are 4 hydrogen atoms in total, and we have the formation of methane molecule. Well, methane is one of the simplest compound formed by carbon and is the major component of biogas and CNG, compressed natural gas. It is widely used as a fuel. So we just witnessed that a covalent bond can be formed by sharing of electrons between atoms of same element, as in the case of hydrogen, or it can be formed by sharing of electrons between atoms of different element, as we saw in the case of methane. Molecules such as hydrogen, chlorine, oxygen, whose atoms are of same element, are known as homoatomic molecules, whereas molecules such as ammonia, carbon dioxide, water, methane, where the atoms are of different elements, are known as heteroatomic molecules. Let us now move on to different types of covalent bonds on the basis of number of shared pair of electrons. Remember the electrons that are present in the common pool between two participating atoms? Your covalent bond can be categorized into single covalent bond, double or triple covalent bond. Let us understand each one of them one by taking few examples, beginning with the single covalent bond. In both the examples that I just explained, I mean that of hydrogen and methane, only one pair of electrons are shared between the two participating atoms. You can see here also in between this carbon and this hydrogen, the two participating atom, only one pair, a pair of electrons is shared. Hence, it is a single covalent bond. Now, we can represent a shared pair of electrons. That means if you have two electrons, they make one shared pair. You can show this by a dash, which is said as a single covalent bond. So, we can represent the formation of covalent bond between hydrogen like this or like this, H, H, and there's a single dash between them. And the single dash means each hydrogen has contributed one electron. For this hydrogen, this is the electron, and for this hydrogen, its participating electron is here. You don't have to show the electrons. A dash automatically symbolizes a shared pair of electrons. So always remember, for a formation of a single covalent bond, you need to have two electrons. Similarly, we can show the covalent bond for methane as C in the center and hydrogen on four sides. Since both the participating atom are contributing one electron, that means they are sharing one pair of electrons. So we can show a single bond between each carbon and hydrogen. So one single bond here, and one here, and one here. So we have four single covalent bond. One, two, three, and four. So if a question comes, explain with the help of Lewis dot structure how many covalent bond are there in methane. So you have four single covalent bond. Let us take few more examples of this type of bond. Say chlorine molecule. Now chlorine molecule has two atoms of chlorine and has a formula Cl2. So first of all we need to write down the Lewis dot structure for chlorine. For that we need to know the atomic number. Chlorine has an atomic number of 17 and has an electronic configuration of 2, 8, 7. 2 electrons in K shell, 8 in L shell, and 7 in outermost shell or the valence shell. So each chlorine atom has 7 valence electrons. So for writing the Lewis dot structure for chlorine, we are going to write down the symbol, and it has 7 electrons. We'll first distribute single electron on all four sides and then we'll start pairing. So we'll begin with, let's say, 1, 2, and 3. So 1, 2, 3, 4, 5, 6, 7. Similarly, we'll represent the other chlorine atom. So we have 1, 2, 3, 4, thereafter 5, 6, 7. Now look, each chlorine atom requires one more electron to obtain the nearest noble gas configuration of that of argon. Now argon has atomic number of 18 and the configuration is 288. So each chlorine atom requires one electron. Let's say it shares one electron. You can see here we have chlorine with 7 electrons. If it shares one electron of this chlorine, its octet will be complete. Similarly, this chlorine, if it shares one electron of this chlorine, its octet will be complete. Let me show it. We have 8 electrons for this chlorine, 2, 4, 6, 7 and 8. And 8 electrons for this chlorine, 2, 4, 6, 7 and 8. So this is your common pool of electron formed by contribution of one electron from each participating atom. So you have one pair of shared electrons. So I can represent this one pair of shared electron by a dash. So you have chlorine, single covalent bond, another chlorine. Well, this pair of electron which is shared or which is in the common pool of electron is known as shared pair of electron because it's being shared between the two participating atoms. And these electrons, you can see these pair of electrons, they are not participating in the bond formation. They are known as lone pair of electrons, LONE, lone pair of electrons, also abbreviated as LP. Now, while showing the covalent bond formation like this by a dash, you may omit lone pair of electrons. I'll suggest you write down the lone pair because it will give you clarity when you talk about bonding in higher classes. But even if you skip, CBSE is going to give you full marks. So we have chlorine with one shared pair of electrons. If you want to show the lone pair, you can show them like this. But since in the formation of covalent bond, these lone pair are not participating, we can omit them. We can simply write down Cl Cl. So we see that chlorine molecule has one single covalent bond. Taking up another example, hydrochloric acid. Although the structure for hydrochloric acid is not mentioned in NCERT, but it is quite simple. Let me do it for you. We begin with hydrogen. Straight away I can write down the Lewis dot structure as H and a dot. For chlorine, we just learned that its electronic dot structure is 1, 2, 3, 4, 5, 6 and 7. Now chlorine requires one more electron to complete its octet. Hydrogen requires one more electron to complete its duplet. So they share one pair of electron. Now hydrogen's duplet is complete and chlorine's octet is complete. You can see here 2, 4, 6, 7 and 8. And for hydrogen 1 and 1, 2. We can represent it by a single dash between H and Cl. So I'm writing here for chlorine the covalent bond as ClCl. I've skipped the lone pairs. For hydrochloric acid, we just learned it is going to be like this. Let's take one more example, water. Now water, the structure is there in your course. Water has the formula H2O. So it is made up of one oxygen and two hydrogen. The atomic number of oxygen is 8 and that of hydrogen is 1. Let's write down the electronic configuration. 2, 6 for oxygen and 1 for hydrogen. So oxygen is in need of 2 more electrons to complete its octet and hydrogen requires 1 more electron. Now since oxygen needs 2 electrons, it can share 1 electron with this hydrogen. So this hydrogen's duplet will be complete and it can share another electron with another hydrogen atom so that the duplet of this hydrogen is complete and octet of oxygen is complete. Let us understand how. So first of all, let us write down the Lewis dot structure of oxygen. Oxygen in the center, it has 6 valence electron. Distribute 1, 2, 3, 4, 4 on all sides and then let's say 5 and 6. It requires 2 more electrons to complete its octet. Let's write down the Lewis structure for both hydrogen atom. We have one hydrogen here with one valence electron. We have another hydrogen atom here with one valence electron. Now look, oxygen is sharing one electron with this hydrogen and one electron with this hydrogen. So the duplet of hydrogen is complete. The duplet of this hydrogen is also complete. Is the octet of this oxygen complete? Let's find out. 1, 2, 3, 4, 5, 6 and one this 7 and the other 8. So oxygen has been also able to achieve the octet configuration. So if we have to simplify this, this can be represented as H, H, and in the center we have oxygen, a bond here, single bond, and a single bond here. So HOH. This is how the covalent bond between water is represented. If in case in higher classes you want to show, you can represent it on top and bottom of oxygen. In higher classes you will learn, actually it is not linear, this is not 180-degree. You will learn the structure of water is something like this, bent structure. You will see this angle, it's called as bent structure. But all this you learn in your higher classes. Let's take one more example of that of ammonia. Ammonia has a formula NH3. Is it homoatomic molecule or heteroatomic? It's going to be your heteroatomic molecule because the atoms are present of different elements, nitrogen and hydrogen. So let's write down the configuration for nitrogen. Atomic number 7, 2, 5. It requires how many electrons to complete its octet? 3. Hydrogen, we all know, has 1 electron and requires 1 more electron to complete its duplet. Now nitrogen requires 3 electrons, right? But one hydrogen can give only 1 electron, so we have 2 more hydrogen. So it can take 3 electrons from 3 hydrogen. Let us see how. Nitrogen's Lewis dot structure, nitrogen in the center, 1, 2, 3, 4, 5. Here I can show this. We have 3 hydrogen atom. I'm putting them or distributing them on 3 different sides of nitrogen. 1 electron for hydrogen each. Now look, if nitrogen is sharing 1 electron with each hydrogen, one this side, one this side, and one this side, hydrogen's duplet is complete. This hydrogen duplet is complete, and this one too. Let's check whether nitrogen's octet is complete or not. So nitrogen already had 5 electrons and it is sharing one with this hydrogen, 6, one with this, 7, and 8. So nitrogen also octet is complete, and we can represent this as N single covalent bond H, single covalent bond H, single covalent bond H. If you have to show the lone pair, which is not mandatory, you can show them here. So this is how covalent bond in ammonia is illustrated. If they ask you how many single covalent bond are present, there are 1, 2, and 3 single covalent bond. Let's move on to the next type of covalent bond, the double covalent bond. As the name suggests, this type of bond is formed when 2 pairs of electrons are shared. Now 1 pair of electrons means 2 electrons. So 2 pairs implies 4 electrons. So 2 pairs of electrons are shared between the 2 participating atoms. For example, oxygen. Now oxygen has the formula O2. Now we are well versed with how to write down the Lewis dot structure for oxygen. We'll have oxygen and 6 electrons, 1, 2, 3, 4, 5 and 6. The other participating atom in the molecule of oxygen is oxygen itself. So oxygen with 1, 2, 3, 4, 5 and 6. Now each oxygen atom, since has a configuration of 2, 6, it requires 2 more electrons. This oxygen atom also and this one also. Let us say they share just 1 pair of electrons, because you do not know whether oxygen has a single covalent bond or double covalent bond in the structure. We begin with sharing just 1 electron. If it shares 1 electron with this oxygen, let's look whether its octet is complete. We have 1, 2, 3, 4, 5, 6, the original electrons, plus 1 from here. So we see that on sharing 1 pair of electron, the octet configuration for both the oxygen atoms are not attained. So this covalent bond structure is incorrect. Let's proceed ahead. We'll again draw the Lewis dot structure for both the oxygen atom. For this one, we have like this, and another oxygen atom we have like this. Now let each oxygen atom contribute 2 electrons to the common electron pool. So I can remove this electron and take it here. Let the pair remain. This is an individual electron, so I'm going to push it over here. So this electron which was here, I've put it here. Similarly, I'm going to remove this electron from here and put it here. Now let us check whether each oxygen atom has been able to achieve the octet configuration. Beginning with this oxygen, 1, 2, 3, 4, 5, 6. 6 the original electrons plus 2 from this oxygen atom. So you have the octet configuration complete. For this oxygen atom also 1, 2, 3, 4, 5, 6. 6 its original electrons plus 2 from this oxygen atom. So the octet configuration for this oxygen is also achieved. Now we represent a single bond formed by two electrons as a dash. So a double bond is represented by 2 dash, 1 and 2. There's oxygen here and this oxygen here. So one bond is formed by two electrons. So two bonds are formed by four electrons. 1, 2, 3 and 4. You need not show these dots. Now you may skip showing the lone pair of electrons, but if in case you want to show 1, 2, 3, 4, 5, 6 and here 1, 2, 3, 4, 5, 6. So this is the formation of covalent bond in oxygen molecule. You can see over here each oxygen is contributing 2 electrons to the common pool of electrons, and thus the covalent bond can be represented as this. Taking another example of carbon dioxide with formula CO2, let's draw the covalent bond for CO2. So we have carbon in the center. Now, why did we take carbon in the center? Because the element which is present singularly, which is present as one, that will put in the center, and rest of them we are going to distribute. Thereafter, when you move in higher classes, you will learn more electronegative element is placed towards the end, when you will learn how do we write Lewis dot structure with rules. So carbon in the center with 4 valence electron, the 2 oxygen atom on both its side. Now oxygen has 6 valence electron, 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. If they share only one pair of electron, that means both the participating atoms share just one electron. Let's see what happens. Carbon 1, 2, 3, 4, one from oxygen 5, one from this oxygen 6. Its octet is not complete. Let's check out for oxygen. 6 valence electron plus 1 from carbon 7. Even its octet is not complete. Let us push one more electron. So let each element share 2 electrons. So this carbon, I can push this electron over here. So you have 1, 2, 3, 4, and this electron, the single electron of oxygen, to this side, because if it is sharing 2 electrons, the other participating atom also has to share 2 electrons. The contribution must be 50-50. It has to be same, it has to be equal. So we have one more electron here. Let's check whether the octet for carbon is complete. 1, 2, 3, 4, 5, 6, 7. 4 original, 5, 6 and 7. Its octet is not complete. Let's check out for this oxygen atom. 1, 2, 3, 4, 5, 6. 6 original electrons and 2 from here. Its octet is complete. Let's check out for this oxygen atom. 6 original plus 1 from carbon. No. So what next? These participating atoms will also contribute one more electron each. Let this electron go here and this electron come here. So now we have 2 electrons being contributed by both the participating atoms. Let's check out whether the octet for carbon and this oxygen is complete. Carbon 1, 2, 3, 4 original, 5, 6 from this oxygen, 7, 8 from this oxygen. So its octet is complete. Coming on to this oxygen atom, 6 original plus 2 from here, carbon 8. So its octet is also complete. So we can represent it by dashes. How? Carbon in the center, double bond with this oxygen atom, double bond with this oxygen atom. This is covalent bond formation in carbon dioxide. If in case you want to show the lone pairs, which is not mandatory, 1, 2, 3, 4 and 1, 2, 3, 4. So this is the covalent bond formation in carbon dioxide. Another important example of molecule illustrating double covalent bond is ethene, which is commonly called as ethylene. It has a formula of C2H4. When we'll talk about the compounds of carbon and hydrogen, we'll study about ethene also. Let's write down the Lewis dot structure and show the covalent bond in ethene. We have 2 carbon and 2 hydrogen. Up till now, we were having at least one single participating atom. The rest were 2 or 3. Here we have 2 atoms of carbon and 4 atoms of hydrogen, right? So let's start with writing the Lewis dot structure. We have carbon 1, 2, 3 and 4, and we have hydrogen with just 1 electron. Now my dear students, when you have more than one carbon atom, you have to show a minimum of one single covalent bond between carbon atoms. What does that mean? Let me show. We have 2 carbons, so one here with 4 electrons, 1, 2, 3 and 4. This is the second carbon atom with 4 electrons, 1, 2, 3, 4. So at least a single bond has to be formed between carbon atoms. Okay, now where do we place hydrogen? Let's find out. First of all, let us check if only a bond is formed between this carbon and this carbon, whether their octet are going to be complete or not. 1, 2, 3, 4 and 1 here 5 not complete. 1, 2, 3, 4 and 1 here 5 not complete. So let's push one electron here. So this comes here and this comes here, right? So now the structure will be something like this: 1, 2, 3 and 4, 1, 2, 3 and 4. Is the octet complete? 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5, 6. No. Let's push one more electron here. This here and this here. So it becomes 1, 2, 3 and 1, 2, 3. Let's see, octet is complete. 1, 2, 3, 4, 5, 6, 7. No. 3 and 4, 5, 6, 7. No. Let's push this electron also here and this one here. So we have C 1, 2, 3, 4 and C 1, 2, 3, 4. Is the octet complete? For this carbon 8 electrons, yes. For this carbon 8 electrons, yes. But is this practically possible? No, you cannot have more than 3 shared pair of electrons between the two participating atoms. But why is this not possible? See, 8 electrons coming close together, right? There will be tremendous repulsion because like charges repel. And if they are going to repel each other, it will not allow these carbon to come close together. The molecule will be highly unstable. It's not going to come close together because the repulsion between 4 pairs of electron is tremendous. So you cannot have more than 3 pairs of electrons shared between two participating atoms. Always remember this. So now let's move on to completing the octet of carbon by these hydrogen atoms. So let us again write down the Lewis dot structure for both the carbon atoms. See in the center 4 electrons and see in the center 4 electrons, right? We have 4 hydrogen atoms. Let's provide equal number of hydrogen to both the carbon atoms. So 2 each. 1 hydrogen I'm putting here, 1 here. You can put this here itself on this side, no problem. For this carbon atom, similarly 1 hydrogen here and 1 here. Let's see whether the octet and duplet for carbon and hydrogen respectively are complete or not. So this carbon atom 4 here, 1 from this hydrogen 5, 1 from this hydrogen 6 and 1 from this carbon 7. It is still one short of octet configuration. Now it has 4 valence electron. 3 of them are already participating in the bond formation. So this one is there. I can push it here, right? Similarly, this one is here. I can push it here. So you will have the 4th electron here and for this carbon atom 4th electron here. Now let's see whether the octet for this carbon and duplet for all 4 hydrogens is complete or not. Let's check up with hydrogen first. Duplet complete. For this hydrogen duplet complete. This one is also complete and this one is also complete. Come on to this carbon atom. 1, 2, 3, 4, 4 original electrons. 2 from this carbon atom 6, 1 from this hydrogen 7, 1 from this hydrogen 8. So its octet is complete. Moving on to this carbon atom, 4 original valence electron, 2 from this carbon atom 6, 1 from this hydrogen 7, 1 from this hydrogen 8. So in total 8 electrons. So even the octet for this carbon is complete. If I have to simplify this, I'm going to represent double bond carbon, single bond hydrogen, single bond hydrogen, single bond hydrogen and single bond hydrogen. So you can see this is a double covalent bond and here you have single covalent bond. So 1, 2, 3, 4. In ethene you have 4 single covalent bond and 1 double covalent bond. Moving on to the next type of covalent bond, the triple covalent bond. I'm sure now you'll be able to define why it is called as triple covalent bond, because it is formed when 3 pairs of electrons are shared. 3 pairs implies 6 electrons. So 3 pairs of electrons are shared between the two participating atoms. Example, nitrogen. You can see over here 3 electrons from this nitrogen and 3 electrons from this nitrogen are shared in the common pool of electrons, and triple covalent bond is represented by 3 dash. 1 dash is equal to 2 electrons, 2 and 3. So 3 dash are equivalent to 6 electrons. If in case you want to, you can show the lone pair of electrons on the nitrogen atoms respectively. Let us understand why nitrogen forms a triple covalent bond. So we have one nitrogen atom here with 5 valence electrons, 2, 3, 4 and 5. We have another nitrogen atom with 5 valence electron shown like this. Let us see whether the octet is complete if they share just one electron. 5 here and 1 6, not complete. Let's push this electron here. So we have nitrogen 1 2 3 4 5. Similarly, we push this electron here. We have nitrogen 1 2 3 4 5. Let's see whether the octet is complete. 5 here, 6 7, not complete. 5 here, 6 and 7, not complete. Let's push one electron here in the center again. Let them contribute one more electron. So we have nitrogen with 3 electrons in the common pool of electrons and 2 here. Similarly, this nitrogen with 3 electrons and 2 electrons here. Now let's find out whether the octet is complete or not. 1 2 3 4 5 6 7 8. So 5 original and 3 from the electron contributed by this nitrogen. 8 complete. Coming on to this nitrogen, 5 original and 3 from this nitrogen atom. So octet complete. I can represent it by 3 dashes representing a triple covalent bond. Now when we know the different types of covalent bonds, let us also try and understand what do we mean by covalency. Covalency actually is the number of electrons which an atom shares with other atoms in the formation of a covalent molecule or compound. What does that mean? Let us take the example of hydrogen. We saw there each participating atom contributes or share one electron, right? So covalency, number of electrons which an atom, here the atom is hydrogen, shares with other atom. The other atom is also hydrogen in the formation of a covalent molecule or compound. It's a hydrogen molecule. And how do you represent that covalent bond? Like this. So each atom is sharing one electron, and therefore the covalency for each hydrogen atom is 1. In case of oxygen, each atom is sharing 2 electrons, and therefore the covalency of each of the oxygen atom is 2. Nitrogen we just did that each nitrogen contributes 3 electron, and therefore the covalency of each nitrogen atom is 3. Coming on to the chlorine molecule, each chlorine atom is contributing or sharing just 1 electron. So covalency for both chlorine atom is 1. Let's finally talk about water. In water, the molecule I have represented like this, HOH. Oxygen is sharing 2 electrons. So the covalency for oxygen is 2. Each hydrogen atom is contributing just 1 electron, and therefore the covalency for each of the hydrogen atom is 1. Let us now put to test what we have learned in this video by answering the following exercise and in-text questions from NCERT. The first question says, what would be the electron dot structure of carbon dioxide which has formula CO2? You can refer to the explanation part to see the electron dot structure for carbon dioxide. Moving on to the next question, what would be the electron dot structure of a molecule of sulfur which is made up of 8 atoms of sulfur? See, in your metals and nonmetals chapters, you've not been taught about the structure of sulfur. So here you have been provided the hint that sulfur is a molecule. It is made up of 8 atoms of sulfur. Like hydrogen is made up of 2 atoms of hydrogen. Similarly, sulfur is made up of 8 atoms of sulfur. So the formula is S8. Now what do they give you as a hint? The 8 atoms of sulfur are joined together in the form of ring. Ring means you have to draw the Lewis structure or the electron dot structure in such a manner that a closed structure, a closed ring is formed, right? So we have sulfur. First of all, let us write down the Lewis dot structure for sulfur. The configuration for sulfur is 286. Why? Because the atomic number for sulfur is 16. So you have 6 valence electron. So I'm writing sulfur and 1, 2, 3, 4, 5 and 6. The valence electrons of sulfur around the symbol of sulfur, right? Now we have to make a ring. We'll make something like this, S, S, like this 3, 4, 5, 6, 7 and 8. That means we are making an octagon, right? So it's a ring now. Now one bond means how many electrons? 2 electrons, one from this sulfur and the other from this sulfur, right? Now look at this sulfur, 1 electron here, 1 electron is sharing with this sulfur and the remaining 4 electrons. So 1 and 1, this we have shared, it has still 2 lone pair of electrons. We are going to put them here, right? And the electron for this sulfur I am showing by a different ink. Let's see whether the octet configuration for this sulfur is complete or not. So 6 original electrons, 1, 2, 3, 4, 5, 6. One from this sulfur and one from this sulfur. So 6 plus 2, 8. So its octet configuration is complete. Similarly, we can make for other sulfur also. So I'm going to show all of them by saying like this. If you don't have to show the electrons on this bond, it's perfectly okay, right? So we'll make it like this. Now, since they have not asked you covalent bond formation but electron dot structure, so you're going to show all these bonds by dots also, right? So the correct structure for electron dot structure of sulfur will be S, S. You make an octagon first, that will be easy, and then all electrons by dots. Make like this because one bond is equivalent to two electrons. So first show by bonds, it will be easy, then convert them into dots. So this will be the electron dot structure of sulfur molecule, which comprises of 8 atoms of sulfur. When you move to higher classes, you will see sulfur has a crown shaped structure like this. So one sulfur here, one here, one here, one here, one here, one here, and one here. So total you have 2, 3, 4, 5, 6, 7, and 8. So sulfur also has crown structure. So some students can make it like this. Even that is perfectly okay. But all the bonds have to be replaced by your electron in dots. Coming on to the next question. Ethane with the molecular formula C2S6 has how many covalent bonds? So for that you should know the bond formation or the covalent bond formation in ethane. How it is? So let me draw carbon in the center and 6 hydrogen. Let us distribute them equally amongst both the carbon atom. So we have 3 hydrogen atom per carbon atom. Now each carbon has 4 valence electron, 4 electrons for this carbon, and each hydrogen is going to have 1 valence electron. Clear? Let's check whether the duplet for hydrogen and octet for each carbon is complete or not. Hydrogen now has 2 electrons. Here also, this one. So all hydrogen have their duplet complete by sharing 1 electron with carbon. Let's look at this carbon atom. So we have 4 valence electron of carbon atom and 1 from this carbon, 1 from this hydrogen, 1 from here and 1 from this hydrogen. So 4 plus 4. 8 electrons for this carbon is complete. Now looking at this carbon atom, it has 4 valence electrons original and then 3 from each hydrogen and 1 from this carbon. 3 plus 1, 4. So it's also octet is complete. So if I have to show in the form of bonds, because we have to find out here how many covalent bonds are present. Let's simplify this. Carbon, single bond here, and with each hydrogen atom it has a single bond. Let's count the number of covalent bonds. 1, 2, 3, 4, 5, 6 and 7. So your correct answer is answer number B, 7 covalent bonds. Let's move on to the next question. Explain the nature of covalent bond using the bond formation in chloromethane. Now student, I'm putting a star mark on this question. Why? Because as per CBSE revised syllabus, the nomenclature of functional group is not present in your course. But still in the exercise you have a question related to covalent bond formation. So to be on safer side, I would suggest you also learn the formation of Lewis dot structure or formation of covalent bond for chloromethane. This is called as chloro from Cl and methane. Don't worry students, I will be teaching you all the deleted portion also from this chapter carbon and its compound. So you can refer to those videos and do this question very easily. Coming on to the structure, chloromethane. Now we have chlorine with how many valence electrons? 7. And we have carbon and then 3 hydrogen. Now each hydrogen has 1 valence electron. Let us check out whether the duplet for hydrogen is complete and octet for carbon and chlorine are complete or not. So hydrogen has 2 electrons, one its own and the one it is shared with carbon. This hydrogen also's duplet is complete. Here also the duplet is complete. Now carbon has 4 original valence electron plus 1 from this hydrogen atom, 1 from here and 1 from this hydrogen atom and 1 from chlorine. So 4, 3 and 1. So total 8 electrons. Coming on to chlorine, chlorine had 7 valence electron and 1 from this carbon. So it's also octet is complete. Let's simplify this. We have carbon single bond hydrogen, single bond hydrogen, single bond hydrogen, and chlorine. If in case you want to, you can show the lone pair of electrons on chlorine. Well, let's look at the question once again. It says, explain the nature of covalent bond using the bond formation in CH3Cl. So you've shown the bond formation in chloromethane. Explain it briefly and then finally write down the nature of covalent bond in chloromethane is single covalent bond. And how many single covalent bonds are present? There are 4 single covalent bonds, 3 between carbon and hydrogen and 1 between carbon and chlorine. Let's move on to the next question. Draw the electron dot structures for ethanoic acid, hydrogen sulfide, propanol, and fluorine. Here to students, I'm going to star mark part A and C because the nomenclature of these compounds, the naming of these compounds, you're going to study in the section of nomenclature of functional group, which stands deleted for students who are going to take their board examination in 2021 due to COVID. But still, I'd suggest to be on safer side, you learn how to write down the electron dot structures for at least those molecules which are given in NCERT. One was chloromethane, the other is ethanoic acid, and the other one is propanol. Let's try and do it. Let's do each one of them one by one, beginning with ethanoic acid. First of all, you should know the formula. Ethanoic acid is your acetic acid which is present in vinegar with formula CH3COOH. So we have carbon in the center. These 3 hydrogen are attached to this carbon. So I'm showing those 3 hydrogen here in blue, right? Now you know hydrogen is going to form always single bond. Why? Because it only requires 1 electron. So we have 1 electron each of hydrogen and 4 electrons of carbon. Carbon and hydrogen, the participating atom, have shared just 1 electron, and hydrogen has been able to complete its duplet. So partly the structure is correct. Moving ahead, I've already told you if we have more than 1 carbon atom, you have to show a minimum of a single covalent bond between the 2 carbon atoms. So you have this carbon atom here. The other one I'm showing in light blue. Here it is. It has 4 valence electron. So let's look at this carbon atom. Now it has 1, 2, 3 and 4 valence electron, 5, 6, 7 from hydrogen and 1 from this carbon atom. So its octet is complete. Let's now see how this carbon is going to complete its octet. So we have 2 oxygen atom, right? And 1 hydrogen atom is attached to this oxygen atom. Let's see how is that possible. So I'm drawing 1 oxygen here and attached to it is 1 hydrogen with 1 valence electron. Oxygen has 6 valence electron, 2 and 2, 4. 1 it is sharing with this hydrogen and 1 it is sharing with this carbon. Similarly, I'm drawing 1 oxygen here. It has 1, 2, 3, 4, 5 and 6 electrons. Let us now find out whether the duplet for hydrogen is complete. Yes, of course it is complete. Whether the octet for this oxygen is complete. 1, 2, 3, 4, 5, 6, 6 original valence electron, 1 from hydrogen 7 and 1 from this carbon 8. So it's also octet is complete. We are left with this carbon and this oxygen. Let's find out. If you look at this carbon atom, it has 4 valence electron, 1 from oxygen 5, 1 from this oxygen 6 and 1 from this carbon 7. It has just 7 electron, but it requires how many electrons? 8 electrons. Look at this oxygen, 6 original plus 1 from this carbon, 7. So what they're going to do, I'm going to push this electron here and this electron here. So we have oxygen sharing another electron with this carbon. If oxygen is sharing 2 electrons, this carbon is also supposed to share 2 electrons. They're here. Now let's find out whether their octet is complete or not. Beginning with this carbon, 1, 2, 3, 4 original, 4 valence electron, 1 from this oxygen 5, 2 from this oxygen 7 and 1 from this carbon 8. So the octet for this carbon is complete. Coming on to this oxygen, 6 original plus 2 from this carbon. So its also octet is complete. Let's simplify this. We can represent it like this: CH, single bond with this carbon atom, double bond with this oxygen, single bond with this oxygen and hydrogen. If in case you want, you can show the lone pair of electrons, but it is not mandatory, right? You have been asked to draw the Lewis dot structure. So you're supposed to draw the structure like this, the one I have told you. You can use a pencil to keep drawing. You can use dots and crosses to distinguish the electrons of two atoms. If you want, you can draw it in the rough first and then fare it out. Coming on to the next one, hydrogen sulfide. So for hydrogen sulfide, we have sulfur in the center, which has 6 electrons, 1, 2, 3, 4. One for this hydrogen, one for this hydrogen. Because hydrogen will always form a single bond, right? A single covalent bond, like this. So duplet of hydrogen is complete and octet for sulfur is complete. So you have H, S, H. That's how the covalent bond is formed between hydrogen sulfide. You're supposed to show the electron dot structure like this. Moving on to the next one, propanol. Now, propanol is your acetone, the nail polish remover, and it has the formula CH3COCH3. So these three hydrogen are bonded to this carbon, and these three hydrogen are bonded to this carbon, and this oxygen is bonded to this carbon. Let's draw the structure. So you have three carbon, and all these three carbons have to be attached with each other with a minimum of single covalent bond. Let's draw. So we have first carbon atom, I'll mark it as 1, 2 and 3. The first carbon atom, it has 4 valence electron. Then the second carbon atom, it too has 4 valence electron. The third carbon atom and the 4 valence electrons. Let me draw now hydrogen. So hydrogen always forms a single covalent bond. So I'm going to draw like this, right? So duplet for this hydrogen is complete, this one is complete, and this one is complete. Let's check the octet for this carbon. 4 original valence electron, one from this hydrogen, one from this hydrogen, and one from this hydrogen. 7, and 1 electron from this carbon. So the octet for this carbon is complete. Let's move ahead. We have carbon, and attached to this carbon is oxygen. So I'm going to show oxygen over here. 1, 2, 3, 4, 5 and 6. Let's look at the octet for this carbon atom. 4 its original, 1 from this carbon atom 5, 1 from this carbon atom 6, and only 1 from oxygen, so makes it 7. Similarly for oxygen we have 6 here and 1 from this carbon 7. So what to do? We can push this electron because this is in bond formation with this carbon, so we cannot push this one electron here. This electron we are going to push here and this one here, something like this. Alright. So we will have 2 electrons contributed by oxygen and 2 electrons contributed by this carbon. So now the octet for this oxygen is complete, 6 original, 2 from this carbon. And look at this carbon atom, 1, 2, 3, 4, 4 original valence electron, 1 from here, carbon 5, 2 from oxygen 7 and 1 from this carbon 8. So 8 valence electrons here. Moving further, we have prepared the electron dot structure until here. Now we have 3 more hydrogen attached to this carbon atom. Let me draw 1, 2 and 3, each with 1 valence electron. The duplet for hydrogen is complete, all of them. And let's look at this carbon atom, 4 original valence electron, 3 from each hydrogen atom, 4 plus 3 7, and 1 from this carbon atom, makes it total 8. So its octet is also complete. So this is the electron dot structure of propanol, which is commonly called as acetone, the nail polish remover. We can simplify it as C and C, 3 carbon atom, and then you have 3 hydrogen here, 3 hydrogen here, and oxygen is attached with a double bond with this center carbon atom. Finally, we have fluorine. Fluorine is just like chlorine. Why? Because they belong to the same halogen family. So fluorine, one here, it has 7 valence electron, 1, 2, 3, 4, 5, 6 and 7. The other fluorine atom with 7 valence electron, 1, 2, 3, 4, 5, 6 and 7. Each require one more electron to complete its octet. So they share one pair of electron. Octet for this fluorine is complete, octet for this fluorine is complete, and this is the electron dot structure for fluorine. You can simplify it further as F single bond F. My dear students, I will advise you that you go for a lot of written practice when you're learning electron dot structure. The more you practice, the more command you will have in writing these structures. With this, I come to the end of this video. In my next video, we will learn properties of covalent compounds. So my dear students, stay tuned to my channel. Do please spare a moment to give this video a thumbs up. And don't forget to share it with anyone who you feel might benefit. Thanks for watching, and until next time, take care. Do follow social distancing. but remember to stay bonded.